Okay, thank you very much, Vinod. And I would like, first of all, to thank Manas, Vijay, and the other organizers for the invitation and for setting up this very nice workshop. Today, I would like to tell you two stories about dissipative quantum phase transition in light matter system. Let me give you a little bit of background. As a condensed matter theorist, my point of view on light is that it's usually used as a probe to study electronic properties of materials, and I'm pretty used to that. In cold atoms as well, you can think of the very same point of view. Instead, what I would like to talk about today is the possibility of studying quantum many-body physics with light, which means that the excitation which are responsible for collective phenomena have a strong photon-like character. And the key idea to get there, as we heard a lot during these 2 weeks, is the idea of cavity quantum electrodynamics or circuit quantum electrodynamics, namely trapping photons into high-finesse resonators and have them interact back and forth with nonlinear elements in such a way to enhance the entanglement between light and matter. And there are several ways of doing that, and in my talk I will have mostly in mind solid-state version of this optical experiment, so called Circuit-QED. If you want to think about energy scales in the system, you have to first of all think about frequencies of your photon mode and your qubit or your atom, and some coupling between them, which is typically going to be much smaller. And these systems are intrinsically open, so they are subject to dissipation either in the qubit or in the photon. And you talk about strong coupling regime when these two excitations are mixed, and so the coupling is much larger than this line width. So as a theorist, if you want to start write down some model that describes this very basic unit, you can go back to Isaac Rabi in the 30s and think of the simplest thing you can do is take an harmonic oscillator and hybridize it linearly with the most nonlinear object that you can do in quantum mechanics if you want, which is a two-level system. And the physical origin of this coupling is just dipole coupling between the electric field and the dipole moment of the atom. You might have seen this model often in the so-called rotating wave approximation, in which you essentially rewrite this light matter coupling in these two ways, where there are terms which conserve excitation and terms which do not conserve excitation, and you trash those away. And this is so-called Jaynes-Cumming Hamiltonian. And let me just give you basic physics which is behind this model. So this linear hybridization between photon and qubit makes very easy to find the excitation of the system. These are so-called polaritons, so mixed light matter particles. And the degree of mixture is, of course, given by how far away they are in frequency. And the important point is that if you look at the spectrum of this model, due to this linear coupling, you get that the usual harmonic oscillator ladder now gets corrected by a square root of n, so the levels are not anymore equally spaced. You can see this in Circuit-QED experiment under driving. Another way of saying the very same thing that was also connects to what Ashish was talking about in his lecture is that essentially you can write down some effective photon Hamiltonian if you get rid of the qubit, and this photon Hamiltonian will be nonlinear. So the photon inherits some nonlinearity out of the coupling with this light. And you can see this in transport-like experiment when you look at transmission as a function of bandwidth, and instead of seeing some linear transmission, you see some steps which are essentially signature of photon blockade. Okay, so this basic unit that I just discussed is, in a way or another, the key building block for a series of platforms to study then many-body physics with light. And we have learned about exciton polarized condensate and or cold atoms in optical cavities by Jonathan. What I will have mostly in mind are two settings. that are based on Circuit-QED, either the idea of coupling these units into arrays, and this is something that started in Princeton, but now there are experiments in Chicago, in Paris, and in other places. On the other hand, another way, as Nicolas was telling us this morning, another way to do many-body physics with the system is to structure the environment to which the qubit is coupled, and this can be done in several ways, either coupling the cavity to some complicated quantum dot source drain voltage bias system, or to some transmission line, as Nicolas was talking about. So overall, these systems are just platforms to study open quantum many-body system, and we have heard that these are kind of very interdisciplinary systems that kind of cut across several fields. And the question that you would like to understand are, okay, what is the interplay between the coherent many-body evolution and the dissipative evolution of the system? Can we have a phase transition which is kind of emerging out of the interplay between these two aspects? And what is the universality out of equilibrium of this dissipative phase transition? Or even you can ask how the bath and the environment shape the system properties, and what's the somehow connection between having a Markovian and a strongly non-Markovian environment. So I will discuss more in detail some of these questions here, focusing on two specific examples. In the first case, I will talk about the Dickie model, which is probably the simplest light matter model that exhibits a phase transition, a superradiant phase transition, and study how the presence of a non-Markovian dissipation will change qualitatively the physics of this phase transition. And in the second part, I would like to go and move toward lattices of Circuit-QED that I was mentioning in the introduction, and study full many-body driven dissipative phase transition in this system. Okay, so what is Dickie superradiance, and how should I think about it? We have heard of that in Jonathan's talk. Here the idea of having many two-level system embedded into a large cavity, and again coupled through dipole interaction to one mode of the resonator. And there are several ways of engineering this sort of coupling. From the point of view of the many-body physics, this model exhibits a symmetry, you see, which is a discrete symmetry. You see that the photon field can be flipped by a sign, and the two-level system operator as well. So this Z2 symmetry can be spontaneously broken if you increase the light-matter coupling sufficiently large, and this is what is called a superradiant phase. So this model was introduced a long time ago and studied mainly by Apple-Leap for the first time in this condensed matter context. And you can easily understand the physics that I was just describing. If you look at the excitation spectrum of this model, you will have a branch that will go soft at this critical point. And it's quite importantly, if you look at the phase diagram as a function of temperature and light matter coupling, you see you have this order phase where the system is superradiant, and essentially all the photon becomes coherent and the two-level system polarized. And as you increase the temperature, you just disorder this easing phase into a normal phase. So you can start asking what happened when you now open the system to the environment, and people have looked this motivated mainly by cold atom experiment. And so in that context, you think about Markovian environment, and you couple your Dickie model with some Limblard path. And the model still maintained this intrinsic phase transition, but if I now going to plot the phase diagram as a function of light matter coupling and coupling to the bath, you'll see that there is still a normal and superradiant phase, but this phase diagram looks very much similar to what you would have at finite temperature. Indeed, there is even a sense in which you can quantify this by saying that the system develops some sort of effective temperature. So you see that if you increase light matter coupling, here you essentially disorder your superradiant phase. Now, you might wonder whether this is a generic scenario with dissipative system, or if you can engineer a situation in which something different happens. So one route for doing this is, of course, if you think about solid-state environments, is of course playing with non-Markovian
non-Markovian bath. So bath which has a spectral function which has some interesting structure at low frequency. So as I was saying, as also Nicola talked about, this model was studied quite a lot in the context of single spin coupled to a bosonic environment, the famous caldera legate. And essentially the physics is that when you couple this qubit to the environment, the physics of the system is strongly affected in the sense that you can go, if you think about this two-well picture, you can go from a state in which you are completely delocalized between the two well to a state in which you are frozen in one of the two, and essentially you break this local Z2 symmetry. So now the question is, what happened when you study this Dickie model here? So many two-level system coupled to a cavity and coupled to a non-Markovian bath. What happened when you study? What happened to this model in presence of this non-Markovian environment? So you can compute the susceptibility to a coherent drive, which is a sort of measure of how the system will react to an external perturbation of the order parameter. And if you do this calculation and get the phase diagram, you find a result which I first find pretty interesting. So I'm plotting again light matter coupling, coupling to the bath as a function of light matter coupling. And here you see that the phase diagram is qualitatively different. So those lines bend leftwards, while as I'm again recalling here, if you have a Markovian bath or if you have a finite temporal bath, you actually would do the opposite. And if you change the properties of the bath, you see this line moves a little bit, but it's still there. So what it's telling you is that in some sense, superradiance here is induced by a coupling to a bath. Again, probably for some of you, this is not surprising at all, but there is a very nice way, I think, to connect this physics to really the Spin-Boson one, because you can convince yourself if you if you integrate out essentially all the bosonic modes, that this Dickie model is nothing but a large spin, or a spin S, which is coupled to a bath, which is non-Markovian because essentially mediated by the cavity photons. So the cavity photons are mediate a bath which is non-Markovian for the two-level system. And now in this language, it's clear that when you increase the coupling to the bath, this large spin will order. And you can ask how actually the two regimes are connected. So how the large thermodynamic large n to infinity limit smoothly connects to the Spin-Boson case. And this can be worked out using some ansatz for the wave function, very similar to what also Serge Florence and collaborator used for the Spin-Boson. And essentially you can see that this phase transition survives at any n. So there is a family of dissipative phase transition. So this is again the usual phase diagram, light coupling to the bath versus light matter coupling. You see there is a phase transition for any n, and this would be the Spin-Boson result. And as you increase the size of your spin from being a truly quantum object to being a macroscopically large object, this phase transition would smoothly evolve, but would stay there, and this would be the if you like, mean field limit that were finding at the beginning. So this is an example of something that is generally non-Markovian, and such a phase transition in finite n would never happen if the bath would have been Markovian. Okay, so this tells us a little bit about the effect of the environment, and in the rest, in the 20 minutes that I'm left, I would like to move now to discuss the physics of our arrays of CQED lattice and the physics of phase transition which emerge in presence of drive and dissipation. So the setup they have in mind really is motivated by experiment in Andrew Hawk lab. So you think of coupling these CQED resonators into networks where the photon is able to hop around this network and is experiencing nonlinearity on each side, which has, for example, the form of Jane's coming that I introduced before, or some sort of Bose-Hubbard, as we said, this photon would inherit some nonlinearity from the qubit. So if you see this Hamiltonian, you might think, okay, this is nothing especially new, in the sense that, okay, there is a model on a lattice with bosons that interact and hop around. So this seems very much similar to what people have studied for what concerns Bose-Hubbard physics and cold atoms. and in general other bosonic massive quasi-particles. But what you have to keep in mind is really the importance of being a photon, which means that these boson particles are not conserved, and the way they interact with the environment is non-conservative. Another way of saying this is that photons have zero chemical potential. So the density of your photon gas is not fixed, but is rather has to be established by a balance between drive and dissipation, or by a balance with interaction strength. So the big question here, I think, in all these arrays is how you can engineer a finite density of photon in your system. So the way that that we have explored in recent years is either, as I said, effectively increasing the light-matter coupling using some Raman driving. This is something I would be happy to talk about offline. But today I would like to tell you something which is more new, and it's actually being finished up right now, and it's about balancing drive and dissipation in fully out of equilibrium system. So the minimal model I want to consider is again this nonlinear interaction for the boson on site with hopping, but now I want to add losses, and I want to add some drive. And the question that I'm after here is what is the many-body non-equilibrium steady state of the system? Can I stabilize a Mott insulator of photons? And what is the dynamics? What are the transitions that I can see in this model? And just as a reminder, this model in equilibrium has been studied very well, going back to the famous Fisher paper in the late 80s. And there are essentially two phases. One phase at very weak hopping, so essentially when these sites are almost weakly coupled, this phase is in insulating phase, it's gapped and it's incompressible and incoherent, so this would be the Mott insulator. But as you increase this rate between hopping and interaction, this Mott insulator becomes unstable towards superfluidity, which essentially means that the system becomes coherent and breaks the U1. And the field theory, the critical theory of this model has been really well understood, the phase diagram, the universality, and so on. What happens in the driven-dissipative case instead is completely open, and there is an important difference, again, traced back to the nature of the photon. There is a U1 symmetry in the problem, but there is no conservation of photon number. So you might wonder, first of all, what happened to all these Mott lobes, which are really linked to the incompressibility and the integer filling of that phase. So to understand this question, the first thing you have to ask is how I'm going to drive these bosons out of equilibrium. And the first thing you might think of is to just add a coherent drive everywhere. And of course, this coherent drive, it's not really useful here, because a coherent drive is just fixing a phase to this photon. And if you like, it's explicitly broken the symmetry that you would like actually to preserve. So the coherent drive is not really doing what we want. Instead, what we can think of, which is very similar to what people do in accident polaritons, is do some sort of incoherent pumping. So a pumping which puts photon, but not, but with essentially with a free phase. So this can be realized, for example, in circuit-QED by just incoherent broadband driving with some finite bandwidth noise. And this was essentially the setup that showed Photon Blockade that I showed earlier about Photon Blockade. So you can describe this noise in terms of a master equation, and I'm going to consider this sort of setup, as well as a recent proposal in which essentially you can tune these rates of input and output to target a cold, almost zero temporal state. But as we'll see, the results I'm going to discuss don't change much whether you consider this kind of drive or this kind of drive. So the first thing that it's important to discuss is that once you use this drive to put photons into the lattice and you measure number of photons as a function of pump bandwidth, you see a staircase, which is again a signature of Photon Blockade. Now, of course, these plateaus, and whether these plateaus really represent states at integer filling or not, is a bit of a delicate question, because at the end of the day, this system is still open and dissipative. So if you really, depending on which drive protocol you use, you can end up into an incoherent mixture of photons, which has different weight, and these weights are all fully tunable. So by increasing strength of the drive, you can actually go to a state which has almost integer filling. So this is already promising for establishing a Mott insulator, having integer filling on site. And of course, this cavity, this single site cavity, is completely incoherent. Now you want to ask what happens when, on top of this drive and dissipation, you kind of switch on some hopping between this cavity and allow photon to tunnel around and possibly build up some spontaneous coherence. So we want to study the time evolution of the system to see how this coherence develops in time, first of all. And so we do this by treating the full Hamiltonian into a mean field decoupling. And this mean field decoupling means that you are solving a single site problem in the presence of a time-dependent field. So what we plot here is the amplitude of the coherent field as a function of time for very weak hopping. So you see here you have oscillation, which in the long time limit decay to 0, which tells you that for weak hopping, this incoherent phase is robust. So this Mott insulator, quote unquote, is robust. And it's very interesting to see the shape of this oscillation. So you see there is a very large frequency, omega star, and then there is a slow frequency, delta omega, and overall relaxation time. So I split these two in this way for a reason that will become clear. But essentially, as you increase this hopping and you increase the tunneling rate between cavities, you see that these two time scale, these two energy scale, behave quite interestingly. And at the critical point, you have a diverging relaxation time and the frequency going soft. So essentially, this is telling you that this Mott insulator is stable until some critical J, but above the J, the relaxation time diverge, and there is a frequency going soft. What happens at the critical point is that essentially the stationary state is lost and the system enters into a limit cycle. And this limit cycle is maintained at the frequency that essentially is smooth at the transition, is this omega star that I was mentioning about. So if you further increase the hopping and you enter into the what we can call non-equilibrium superfluid, so you have a phase which has a amplitude of coherence which is different from zero and oscillation. You see amplification which is eventually saturated, and so you can extract some average value or long time average value of this order parameter, and you see that as a function of distance from the critical point, it goes to 0 as you expect at the phase transition. So the superfluid emerge here as some sort of limit cycle phase in which this oscillation happens at a frequency which is not imposed by your coherent drive, but is a frequency that is internal, somehow emergent from the interaction and the balance between drive and dissipation. You can ask whether this frequency can be eliminated, and that's something, meaning if you can go into some rotating frame and get rid of that. That's something we checked, and you can do that, and you can essentially go into a frame in which this problem becomes stationary, which suggests that there might be a description of this dynamical transition that I described purely in the time domain. It might be possible to describe this as a stationary state frequency, finite frequency phase transition. That's what I would like to tell you in the rest of the talk. So first of all, this is the phase diagram that you would get by doing the dynamics. So this critical point as a function of bandwidth of your drive. And so these are the so-called Mott lobes. And of course, you see the physics is very different with respect to what it was in equilibrium. The lobes don't touch anymore J equal to 0. And that's just because the system in presence of drive and dissipation is not susceptible for a very weak J. So what happens what can we say about the universality of this phase transition, and what can we say about the stationary state? So to do this, you have to do something more than just doing a mean field, and I'm not going to enter too much in the details, but there is a way to formulate a Keldysh field theory for this lattice driven-dissipative problem, and this essentially is the first step of some large connectivity limit for the problem. So you introduce an order parameter psi that is essentially the average of your photon field, and you write down this effective action where all the many-body physics is encoded in this function here. And this is what people would call, in field theory, generating function of all the connected dynamical correlation. It's something that looks pretty nasty, but you can do an expansion and write down a field theory out of this. And what enters in these field theories are the Green's function of this local Markovian problem. So the one particle Green function control the quadratic part of the action, the two particle Green function control the nonlinearity. So by looking at these guys, we can learn quite a lot about the phase transition, and as I'm going to show, you understand this dynamical instability that I was telling you about. So first of all, we look at the retarded Green function of this single site in presence of drive dissipation and interaction. So there are a bunch of peaks that you can understand if you look at the spectrum of the single site. What it's really important, I would like to draw your attention on, is that this Green function has a zero, imaginary part of Green function has a zero at finite frequency. So this is something that would never happen for a linear system. A linear system would be just, would have imaginary part which is just a nice Lorentzian. This zero of the imaginary part bothered me for quite a long time until I realized it has a quite nice meaning. And the reason is that this guy is nothing but the building block that you need to have in order to compute the susceptibility of your order parameters. So in order to compute how the system responds to a drive, weak coherent drive or weak coherent drive at frequency omega. And if you do this calculation, you realize that this susceptibility at the critical point has a pole which emerges not at zero frequency, as it would be in equilibrium, but at finite frequency, at the frequency omega star, which is nothing but the frequency of the limit cycle oscillation. So this tells you that the driven Mott insulator is unstable toward limit cycle, and this instability emerges as a finite frequency susceptibility which diverge. And you can do a little bit more with that. You can use and look at the Green function of this lattice in this RPA kind of theory, and do the long wavelength small q and small omega approximation. But it's important now that you kind of expand around this frequency omega star, which is really the mode that is going soft. And if you do this expansion, you realize that there are correlation lengths which are diverging at the phase transition as you expect. There is a static correlation length, but most importantly, there is a dynamical correlation length. And this dynamical correlation length is a complex number as a real and imaginary part, which means essentially that there is a critical relaxation time and a frequency going soft. And if you use these ansatz and you plug it back in your action, essentially you get equation of motion which tells you nothing but that the solution I was telling you about, this damped oscillation with fast frequency and slow frequency, is just the saddle point equation of this equation. So in some sense, the Green's function of the lattice encodes the relaxation time and the frequency softening which happens at the phase transition. Okay, with this I think I'm pretty much done. I described two examples of dissipative phase transition which are kind of different in a sense. The first one was strongly due to the non-Markovian bath and the non-Markovian nature of the environment. And I think this is a nice example of a system which can have non-equilibrium criticality, possibly different than equilibrium, just because the bath cannot thermalize the subsystem. And on the other hand, I talked about dissipative phase transition in bosons, which are driven with incoherent drive. And I think one very important feature of this Mott insulator of photons, of driven Mott insulator is that this phase is unstable at finite frequency with respect to coherent drive, and this instability turns into a non-equilibrium superfluid, which is just a limit set. And what I think would be very interesting is to work out more the universality properties of this dissipative quantum phase transition. And before concluding, let me acknowledge, first of all, Orazio Scarlatella, which is a PhD student in Saclay, which is the one that has mostly done the work both on the Dickie Superradiance and on the Bose-Hubbard. And then I would like to thank Saro, Fazio, and Jonathan Killing, and Akan Turesh's group for collaboration on other projects, and a bunch of people for discussion. Someone are also here, and all of you for your attention.
Hello. Yeah. So at some point, I think you showed some a single site, and then you reconstructed the full thing somehow. Yes. Yeah. Yeah. Like, can you explain how to do that?
Oh yes. This would be essentially from this. So you see, this guy here is the Green function of a single site, but then essentially you can compute the so when you do this kind of RPA expansion, you see you have two terms which are quadratic in the order parameter. There is a term which is proportional to the Green function of your single site, and there is a term which is proportional to 1 over j. And essentially, the Green function of your order parameter is just the inverse of that, and that will give you the essentially RPA approximation to the lattice, which is nothing but what I wrote here. So 1 over j plus g is essentially the RPA.
And how did you obtain the single site results?
The single site you obtain by diagonalizing the Limblard dissipator and computing the Green using the quantum regression theorem.
So here every site is sort of dissipative, is it?
Yes. So there is dissipation. You see, there is there is dissipation and drive everywhere in the. You see, there is losses everywhere, and drive. Drive is. So drive is everywhere. So in some sense, the drive and dissipation and interaction enter in this single site problem you have to solve numerically.
I see.
Okay. For the driven-dissipative case, for the single site limit, how different is it from a laser or maser?
No, that's
sorry for this question, but maybe.
No, I think that's a very good question, and something we were discussing also here. I think you mean this?
It looks like self-oscillations.
Yes, I think that's in some sense this is I think this is a good parallel. In some sense, it's a phase which is coherent, and in the time domain it appears as an oscillation. Yeah, I think the lasing is a good way of saying that. Good way of describing this superfluid here. Yeah.
So like a related question, I guess, isn't the analogy even better to kind of like a classical synchronization problem? And could you understand the physics from trying to look at some effective Kuramoto model? Or are there things that are really distinct from classical synchronization? So without the tunnel coupling,
in the sense that everyone starts to oscillate.
So without the tunnel coupling, it's like each site has negative damping, right? That's equivalent, I think, to your incoherent driving.
Yes, yes.
Then the tunnel coupling wants the oscillators to synchronize. So
no, that's good. That might be a good idea. Indeed, I think that when you write down the Keldysh action for the critical theory of that, you will end up in some sort of classical model. So it might be a good.
So there are these kind of universal models of synchronization that maybe you could connect.
No, that's true.
Or if it was different, it would be.
Are these driven or not?
Are those what, sorry?
Driven?
The driving shows up as an effective negative damping, which is equivalent to your
so driving. In some sense they are okay.
Yeah. And is your driving, do you bandwidth limit the drive?
Yes, that's important. Yeah.
Good.
That's important. Yeah, that would be nice.
Yeah.
In every experimental system there will be disorder. So again, for this second driven-dissipative case, I should compare the disorder to J, to U, or to sigma?
Well, good question. So, already in equilibrium, this becomes a very interesting problem, because essentially you have some sort of region here where you have a Bose glass or something. So I guess you want to compare, well, if I guess disorder will be on site, basically because all these frequencies will be of resonance. So I guess you might want to compare it with the local interaction, I guess, to see if this to see essentially in which regime you are. But it's interesting also because to me it's not completely clear whether the this insulating phase is more like a Bose glass or a real Mott insulator, because as I told you, essentially it's very difficult that this phase will be truly incompressible. So just because there is leakage and dissipation, so this might be an insulating phase which still have a little bit of compressibility. So disorder might not be dramatically destroy this, just because this is already a little bit different than the just regular Mott insulator.
I got a little bit confused. Were you able to analyze beyond the mean field?
Well, this is what you would say is RPA. So this is mean field, this is time-dependent mean field, but in some sense, once you get into this Keldysh, so this would be a strong coupling RPA, if you like, which you can call mean field, or you can call mean field plus fluctuation, as you like. But in some sense, this gives you spectral function of the Mott phase that you would not get in mean field. So in standard mean field, you would say the Mott phase is just a bunch of decoupled sites. And from this analysis, you would get green function and finite momentum in the Mott phase, which means that you get entanglement, if you like, from next neighborhood site. So this is beyond the just factorization.
But is this enough to say something about the universality?
No,
So
that's not, absolutely not. But you see, that's why I'm saying, so that's just the first ingredient you need to build up your Keldysh field theory. But you see all these, so if you go back to the Fisher story, you see all this universality business, whether you are at the relativistic invariant point at the tip of the lobe or not, they all comes about because of this coefficient, and this coefficient, they do something funny as a function of chemical potential, right? And these coefficients are just properties of the single site problem. So this already you can get through this theory. Then of course, if you want to do RG, you have to do RG. That's beyond what is here. But so in some sense, what I'm saying is that this is this would be the action one should do RG on, with the coefficient and the microscopic coefficient that are completed by this approach.